So lab 2 is all about making schedules with a little microcontroller, and we'll build a simple traffic light controller to demo this. So this is going to talk a lot about timer 0. So the objective here is to use a timer to actually generate a interrupt, we call it, which is like a little chunk of code that gets run ever so often. So and here, sorry, I was just pulling some of this up. What we have is there's a timer 0 on the microcontroller. So take a look at the microcontroller datasheet, and it basically explains how there's a timer module. And so here's what we care about, which is this little count, TCNT0, and it just counts up, basically. It just keeps going up, so it goes from 0 to 255. It's an 8-bit counter, so that's the maximum value it can have. And then by default, it just wraps around back to 0. But we get a notice when it does this wraparound. So when this happens, we call it an overflow because it's reached the max value. And we run a little chunk of code. So we run a little chunk of code every 256 cycles. So the full counter has some other stuff around it. We actually don't care about most of this right now. So we're not going to worry too much about it. We're only going to look at really this count module itself. To turn on the count module, so we'll then go down to the register sets here, so we can kind of ignore a bunch of this again. And what we care about, so there's a control register A. By default, I think it's more or less good. It has a bunch of stuff disconnected, so we don't care too much about it. What we do care about is in count register B, there's these bits here, and you really want to pay careful attention to these 3 bits because you're going to have to change them because they define the speed at which the counter is running. Because we basically have a 16 megahertz clock, I believe, on this board. And by the way, when you're looking at the board, as a little side note, there's actually 2 crystals on this board. There's one here that's a big one that's used by the USB chip, and this is 12 megahertz. And there's a tiny little crystal here. This is the one actually used by this microcontroller, and this is, I believe, 16 megahertz. So just take a note. I think sometimes I even point out this and have the wrong frequency. So we can measure all these though, so we'll figure out what the actual frequency is in a second here. So this is then divided by, for example, if I use the slowest, 1024, right? So this then gives us a clock that is, if we go 16, 1, 2, 3, 1, 2, 3, it's now only 15,625 hertz. So we now have a 15,625 hertz. But this clock itself, so if we just go for a little detour here, right, what this clock is doing is we have a 15,625. Let's just make this little 15,625 hertz clock. What this clock is doing is it's going into the counter. Right, so this counter counts 0, 1, 2, up to 255, and then wraps around. And it's only on this wraparound event, so remember that it's only on this wraparound event that we run our interrupt service routine, the ISR. So what does this mean? This means our actual ISR speed, so how fast that's running, is 15,625 divided by 256. And this is a different, right? This is now 15,625 divided by 625. Oh wait, 15,625 divided by 256. Is 61 hertz, right? So this is now pretty slow. If we want to have a specific speed, so in the lab, we're going to ask you to run this at every millisecond, so 1,000 hertz. What do we have to do? There's 2 things we could play with, right? We could adjust this frequency here, or we could adjust how the actual count value it's using. So these are the only two things we could adjust, 1 and 2. So 1 was adjusted by the prescale, CS00, CS01, CS02, so that was in the data sheet. This one we adjust by changing what our reload value is. So these are the two ways that you're adjusting how quickly the ISR itself is running. So we'll get into that pretty quickly here, but I just want to point out, and you'll notice these only have fixed values, so there's not too much adjustment you can do. You may need to end up doing a bit of both. So the reload value, what this means is, say we didn't go back down to 0, we can tell our counter, in fact, we can kind of force it to start, right? If it starts at 2, now all of a sudden it's not counting 0, 1, 2 up to 255. It's going 2, 3, 4, etc. up to 255, and we reload it back to some higher value. So by adjusting the reload, we can adjust how quickly that runs. But let's not worry too much about that now. What we're going to do is I'm going to make a new, let's just close this. Make a new project. Timer 2, let's call it. And if you are rusty on this stuff, see the other video on the GPIO setup. Okay, so here's a simple project, and all I'm going to do is I'm going to take a look in the lab, and I'm just going to copy this example in. So this example just has, why is this so difficult? Here we go. Okay. So we have some sample code here. Always double click the main.c to make sure you're editing the file that's being compiled in. Very important. Sometimes people are trying to add new files without realizing they're not actually getting those files into the project. So we're going to add interrupt.h. This interrupt.h gives us this special macro, it's called, which is like a little sort of C shortcut to define an ISR, an interrupt service routine, for timer 0 overflow vector. So now this chunk of code will run every time the overflow interrupt is handled. So by default, we're just going to make this count variable, and it's uppercase C in this example. And every time we just increment the value of count, and then we assign it to port C. So we're actually going to write this out to some hardware. But for this to work, we're going to need some timer setup. So before that, we're using a GPIO register here. We need to set that register as an output. We're then going to turn on the timer overflow TO interrupt enable 0. So you'll notice it goes purple like this, meaning I have a valid symbol. If I made a typo, like I call that T0, then it doesn't go purple. Okay, so we have a valid symbol. We're going to reload it to 0. Set our count value. And then the other thing we're going to do is that 0B register. So this is that in the datasheet I had this CS02 set to 1 and CS00 set to 1. So this is a 1024 prescale, right? So this means, in theory, this code is now going to be run every 16 megahertz divided by 1024 divided by the rate it's overflowing. So this should give us about 61 hertz. Okay. And then we can set interrupt enable. This is really critical. This turns on the interrupts to the system. Okay. So this works. we build successfully. Then all we do, so I got my board plugged in. I've checked that it's coming up as COM3. So I can go here, Tools, Nano Download. We see success. Okay, so what's happening here? Well, not a whole lot, right? Because port C is not routed to anything interesting. What you want to do is figure out where is port C going. Well, if we pull up the little reference diagram, you can see port C is basically A0, A1, A2, blah, blah, blah. So all 7 bits are being used as an output. But what we expect is that, you know, the lowest most bit, for example, is going to be toggling because it's counting up. So as we look at different output bits, so I'm going to use a little oscilloscope here, we should see different data toggling. So for example, we could start with A0. So just take your scope probe and you could put it right onto A0. And what you should have, right, is that especially if you're using a standalone scope, you're going to need a ground connection. So we're going to ground it. And what you might find helpful, because maybe we don't want to hold it on, is I'll get another wire. I'm just going to plug it into this. And then I'm just going to plug that right into A0. So now if we look on the scope, what do we see? That looks nice, right? We see a square wave. What's the frequency of the square wave? You might think, should this be trigger auto? Let's just get this nice trigger. Should it be 61 hertz? Well, it's actually probably going to be half of that. Let's see if we did this right. Or no, double. Because what's happening is, right, it's transitioning, I believe, on the 61 hertz point. So it's toggling. So we see we have a frequency of 122 hertz, or this is running at 8 megahertz. Either way, it gives us a starting point here. So what we would like to do is actually basically get this to a point that we're able to use that count variable to make more interesting main loops, because we could use this count variable to actually store time. So we're going to do a few changes here. So one thing you could do, right, is within this overflow, I said, what if we reset this timer value to something else? So what if it only counts up, say, 200 points instead of 256? Well, now we'd have 16, 1, 2, 3, 1, 2, 3, divided by 200. Now we'd have 78, right? If we want to get all the way up to around a kilohertz, then what we need is we need to actually, we see this should reset somewhere around 15. What this means is I actually start my timer count register 0 much closer to the ending point. So now it's going to reset, and I'm just going to make the compiler do the math. You know, it's going to reset to whatever that value is, the 255 minus 15. So it's resetting it to 240, and it's only going to count a few more values. So if we run this code, let's just see what happens here. Right? Now you can see this frequency's gone way up. So we now have a 1.953 kilohertz signal coming out of this guy. So what would be nice is if you play around enough, you should be able to get this basically running at a kilohertz here. And you might have to play around with the prescale and the reset value. Okay, so what does that get you? Well, we can now make a, let's make this an unsigned int, time, and we'll call it, let's just keep calling it count. So now count's going to increment every time. I'm not going to worry about putting it out to the port. And in our main loop, right, let's say we want to make a LED pattern, something happening with different LED statuses here. So let's make it every second blink an LED. This is what we were doing before. So we're going to change it around a bit. We're going to put port B5 as an output, right? And before what we had is we had port B and we could toggle, right, port B5, just like that. And we need to have a way to delay for a second. So what we want to do is we actually are going to wait for port B, or we're going to wait for that count value to equal 1,000. And so I'm going to say, well, it's not equal to 1,000. Just hang out in this loop, right? So wait until 1,000 has passed. And when it has, toggle the port pin, and we're actually going to set count back down to 0. So we're going to reset the timer back to the start and wait another 1,000 ticks. So you might think that looks good, but there's a few tricks here. So I actually have to do a few little things because of the compiler. So the compiler doesn't understand that these interrupts are going to get called. So we have to use this special keyword called volatile. This tells the compiler that the program flow doesn't just exist inside this loop. Ever so often, this little magic interrupt service routine gets run. So we set the value as volatile. The other thing we have to be a bit careful of is, let's just build this and run it, because you might actually think that it's going to work just fine. Right? And I think it kind of will. And if we go here, right, so you can see this is blinking. It's not, I don't have the frequency right. It's not at a hertz. I haven't gotten that part right, so I've got to go back and tune my timing. If you remember, that was running at like 1.9 kilohertz, right? So this isn't quite right, but it is blinking. But there's a little trick that's kind of bad practice in here. This is that if we look at the disassembly of this, I believe this will show it to me. Well, let's just open a file to get that. Okay, so we can open something called the list file. And so this list file is the actual assembly code, which we haven't really talked about, but this is the low-level code, or closer to the low-level code that the device is running. And the problem here is that there's these load statements that are actually loading the count value from memory. But what could happen is in between these two statements, an interrupt could fire right here. And so this means that our value is changing as we're using it. So that's a little funky, right? So halfway through using the value, the interrupt fires. So what would be a little nicer is if we do something called, it's normally called like an enter critical, but we basically disable interrupts with the CLI and SEI. So disable, turn off interrupts. And this just ensures that while we're touching this count variable, the interrupt's not also touching it. So we avoid it from being double used. We also need to do it for the loop test, but that's a little tricky because if the interrupts are off for this entire loop, it's not going to work because it's never going to exit the loop. So what I'm going to do instead is I'm going to change this logic and just say while true, disable interrupts if count is equal to 1,000, break out of the loop. Turn them back on. And if an interrupt has to fire, it'll fire and keep going. So even though the code worked before, it's a bit risky that it's a bit risky that something could happen. So if we look at the disassembly now, we have this disable interrupt. It touches that count value that the interrupt itself is dealing with, and then it turns them back on. So it's a bit tricky to make sure that we don't have any issues with it. And if this breaks out, it's actually going to keep the interrupts off until they turn back on here. So if you want, you could, change this around to turn them on, but this should work as is. So let's download that. Let's hope I didn't totally break it. And we get the blinking again, right? So even though it's a bit different, even though that looks the same, it is a little bit different, right? So the cool thing about this is now, if you wanted to make a bunch of states, right, you could imagine you could just wait, like, I could just copy this again and say, and wait until 2,000 milliseconds has passed. So then I could wait, or 4,000 milliseconds has passed. And I could do something different here, something different here. So we could basically make this big state machine of going through different times and doing different tasks, which is exactly what the lab is going to ask you to do. But for the timing to work, you're going to have to tune this reload value, and you might have to tune the prescale. So those are the two things you're going to have to play with, and you should be able to get an exact 1 hertz blink, and you should be able to show it on the scope that it is an exact 1 hertz blink. But that's the basic idea behind this lab.